Exactly. And then I'll start the YouTube video. Okay. I'll do it after that. Okay. So welcome everyone to the final talk in our IBM Illinois Discovery Accelerator series of seminars for this year. So we'll be back next year. But for this year, Tamar is our final speaker. It's my pleasure to introduce her today. So Tamar is an IBM fellow and the chief scientist for sustainable computing at the IBM TJ Watson Center. So there she's leading research aiming at drastically reducing the carbon footprint. So that's an important topic if you ever have done the math. So in my group, we do computational material science, and I have estimated that some of the simulations we run equate flight from Chicago to Frankfurt. So and those are simulations that we run on a daily basis. So in other words, this carbon footprint problem is a big problem, and Tamar is working on it. Tamar obtained her PhD at the Technion in Israel in the year 2000, and then she joined IBM in the same year as a staff member and was recognized as a fellow in 2014. So it's my pleasure to welcome Tamar to campus and listen to her talk on the AI problem with energy and what to do about it.
Right. Thank you, Andre. And it's nice being here. Some things you need to know about me. First of all, I had a really hard time getting here today, but you already know that. So I had to stay overnight in Chicago. I'm a chief scientist for sustainable computing. How did I get to be a chief scientist for sustainable computing? My background is actually algorithms and graph theory. I did a lot of work on distributed computing and cloud, but in 2019, I really became very obsessed about climate, and I decided to do something about it. And in IBM research, we started in 2020 a program for climate, and I joined. I helped shape it, and I decided to, within everything that we can do for climate with technology, I'm focused on sustainable computing, which is reducing the carbon associated with computing in general. But there are other areas of research in IBM that are dealing with how to use technology for sustainability, and I'm going to mention some of them. And the other thing I wanted to say is this presentation is based on research contribution from multiple different scientists in IBM research and collaboration, including collaboration with UIUC and with other universities and in open source. So this is a lot of contribution from a lot of different people. I like to look at the bigger picture of things. And so I'm going to mention a lot of work. It's going to be very broad, and I'm going to give you a lot of references. So you can follow the references and read more about some of these topics, and you can spend a lot of time reading them. By the way, not all of them are academic papers. Some of them are blogs that are very technical and are very useful to learn new technologies and to get ideas about research that you can do specifically for the students. I'm hoping to distribute. Please, everyone, mute your phone, mute your computer. I'm hoping to distribute the charts later, so you're going to have the links. Okay, so let's start. I also wanted to give you an idea about what the kind of work that we're doing in IBM research, so that you're going to get an idea of what it is to work in a research lab and so on. So that's another purpose that I have with this talk. Okay, so the two-headed monster. First of all, AI models are getting bigger, much bigger. And as you can see here in this chart, this is a log scale chart. There is like a 10x growth in model size. In every 18 months, I think they grow by like 10x. Okay, and with that, the energy that they consume, it's like super linear, the energy with relationship to the size of the model. So there is AI is exploding. We know it's exploding, and it's consuming a lot of energy. That's the first head of the monster. Okay, and you can see some numbers here. 1,000 megawatt hertz could power an average US home for 100 years, but GPT-4 is for training, it's 51,000 for training GPT-4. So this is a lot of energy that we're talking about here, right? Okay, so what's the second head of the monster? The second end of the monster is that we have reached the end of Dennard scaling. also known as Moore's Law, which means that we're used to a world where every 18 months to 2 years, we get double energy efficiency from general purpose CMOS just by doing miniaturization, just by putting more transistors in a square millimeter. Okay? And that was easy, and we've done it for many years. However, we have reached the limits of physics in terms of what we can do with general purpose CMOS chips. So we're not getting the same energy efficiency improvements that you were used to. So this is the two-headed monster. And what's the result of that? The demand for power, driven in part by the rise of generative artificial intelligence, is expected to grow to a level not seen in generation. Okay, so you see the graph here, and you see that the graph has been flat for many years. For a decade or 2 decades, the graph has been flat. And the graph has been flat. When I say the graph has been flat, it's not that we're not doing more computing. We did more and more and more and more computing. However, the total energy for the data centers in the world stayed flat. And how is that? One is, we talked about it, it's that they're not scaling, it's chips are getting more energy efficient all the time. That ended. 2 is that there are lots of low-hanging fruit technologically that we leveraged. One of them is automation, virtualization, moving to cloud. All of that add the effect of consolidating and being more efficient, okay? And then also technologies that had to do with cooling. So cooling improvements. So maybe you don't know it, but for a data center, the overhead for cooling is very big. PUE, which is the power usage effectiveness, is now down to almost optimal. So meaning almost no overhead for cooling and power distribution. All of that we've already done. So we exhausted all these means, and now we're seeing a huge increase in the energy for data centers. As I said, a lot of it is due to AI. And we really got to that point of tension where, you know, some companies have a lot of money and they want to buy more and more GPUs. They also have a data center for it. But when they go to the power company and the power grid and they negotiate and they say, give us more power, they say, we don't have more power. So it's not that they have the money to buy the GPUs, but they don't have the power to power these GPUs. So we reached that point right now. So that's what's going on. And okay, so it looks like the perfect storm, right? Right, so what are we going to do about it? Dump AI? Do we think that we need to dump AI? Well, maybe we should think again about that. So AI is actually a very good tool. It's actually very powerful and can also be used in order to combat climate change. So we are using AI for adaptation, for example. Adaptation is, okay, we know it's coming now. How are we going to reduce the risk? So one project that we did in IBM is to work with NASA on developing a foundation model that we open sourced to analyze satellite images in order to be able to predict things such as floods, things such as fires, and so on, to reduce the risk. 2 is mitigation. So mitigation, when it comes to sustainability, is all about how we try to mitigate, so try to reduce the greenhouse gas emission in the atmosphere in order to slow down the climate change. And here, we are using AI in order to accelerate the scientific discovery. So accelerating the scientific discovery for things such as sustainable material, finding materials that can replace PFAS, which is forever chemicals that are used in the semiconductor manufacturing process that are very harmful to the environment. We're using it in order to find material that can potentially help us do the sequestration of carbon, so you know what is called as carbon capture. And we're also using it for life science, so you know, to accelerate the time that it takes to find vaccines for I don't know, new pandemics, whatever is going to come on us. You know, after COVID, we've seen it once. We know it's coming again, right? By the way, as I said, I promised you, look at these charts. They're full of links. All of these links, if you're curious about any one of these topics, follow the link, okay? So back to the perfect storm. So what do we do about the perfect storm? Fight it with innovation. And I'm saying fight it with innovation, and I know that some here are going to argue with me that we also need policy and all of that, and I agree with that. However, I'm a scientist, so what I know is to fight with innovation. And the biggest question is, how can we do more computing while spending less resources, energy, and carbon? And my main focus is AI, because this is what consumes all the energy. So we're going to get there. Yes, question?
Yeah, we spoke about reducing the carbon footprint. Why are we relying on things like fusion, which will give us so much energy? We don't have to worry about reducing energy. Instead, we can accelerate that and just keep going as we're going.
Yeah. That could be part of the solution. I mean, we're not there yet, but it could be part of the solution. And I think, and we had this very, very interesting discussion. Sustainability is a very wide area, and there are lots of different things that needs to be teased out. So within that area, there is energy and how we generate energy. And by the way, that chart is about that, okay? Which will absolutely must be investigated with the right expertise. And there is also the area where I'm focused on, which is I want to do computing, and I want to do computing with less energy, because in any case, we're going to need, I mean, until we get to the point where we have so much energy, and that will be great, we need to reduce the amount. This is just like a side note, the difference between energy and carbon. So really what we're interested in, reducing the greenhouse gas in the atmosphere. How we generate electricity, the method that we use is associated with different levels of carbon, right? So coal is the worst. Wind is the best, as you can see here. And by the way, just to show you, this is an electricity map that basically shows us in each area of the world, what is the average CO2 emission for generating electricity, okay? And, okay, not that one. Going back here. And this one is also very interesting. Every state in the United States have a different mix of energy. And this article shows you all the different states and how the mix of energy between the different sources changes. And it changes also over time. So we see more natural gas, for example, and things like this. So it's just an interesting thing to know that it exists. Okay. So back to our scientist. So perfect storm required rethinking. And this is the most important chart that I'm going to show you in this presentation, because it's going to show you the lay of the land, okay? The lay of the land of everything that is not everything in sustainability, but at least everything in AI and green AI, okay? So first of all, hardware architecture innovation. We talked about the fact that Moore's-law is dead, Dennard scaling is dead, so that means everyone are moving to specialization. What's the thing with specialization? Now you have chips that are able to run more efficiently for a class of workloads, for a limited class of workloads, but they can do it more efficiently. So if we can't really improve the general purpose CPU, we can build special architectures for special classes of workloads. Okay, so specialization is big. And then we start thinking beyond the von Neumann bottleneck. What is the von Neumann bottleneck? This is how I learned when I was a student. There is the processor and there is the memory. And there is a instruction point that points to the next instruction to execute, okay? And we fetch the data that we need, we perform the computation. Problem is, the bottleneck is the memory. So when we move data, this is where all the energy is spent. So now everyone are trying to think beyond the von Neumann architecture. What do we do? What kind of architectures we can come up with? And then you go into all sorts of architectures, all sorts of ideas, such as in-memory computing, or bringing the memory to the computer, bringing compute to the memory, and all sorts of ideas like this, space-based architectures, data flow-based architectures, and so on. And they are all a lot of them are optimized for matrix multiplication. We're going to talk about it later. So we're going to talk about all of that later. That gives you sort of the landscape. Why? Because AI. Matrix multiplication has very specific characteristics that can be leveraged in order to build specialized chips. All right, so the next one is AI model innovation. How are we innovating on models? What's the biggest problem with models? The biggest problem with models is that they don't scale. So what's going on there is that a lot of companies have a lot of money, and there is a competition between these companies. And the best way for them to get to the new and fantastic model that is going to amaze the world is to throw more data and more parameters. So now we're in billions of parameters and trillions and a lot of trillions of, I don't know, terabytes of data, right? And because it's the easiest way to see what's going to happen. This is always interesting. However, it's not sustainable, right? So the whole thing about AI model innovation, I think a lot of it is beyond just big. How can we build models that are great and are not that big, so they consume less energy? How do we break the monolith? Now, everyone are about the transformer architecture. Based on that paper, attention is all you need. However, transformer is a very regular architecture. And when you look at our brain is not regular, right? So maybe we need to think beyond transformer. What's next? So there is a lot of innovation on model architecture, and a lot of it is about, okay, how can we be great, but not so big, not consume so much compute and energy. And then there is platform innovation. And platform is the thing that sits in the middle. So think about all these different models and all these different accelerators, okay, that are coming into the picture. The platform sits in the middle. It needs to support training, fine-tuning, inference, and it needs to do that in a constrained environment where you have a set of accelerators and you have energy limits, and you want to run the most computation with these resources, okay? And one of the things we're going to say here, and I'm going to say here, it's not one size fits all. So how do we leverage heterogeneity? And it's not so easy. Like, I can tell you one thing. When I started to work in IBM, I worked on a project that was called Oceano. The idea of Oceano is oceans of servers. They're all cheap and they're all similar. And what do you do if you need more servers? You just allocate more servers. You don't worry about 20% utilization because they're so cheap, okay? And then you allocate based on the load, and we build automation to allocate based on the load. So we have Coca-Cola and Pepsi, and we allocate servers. Okay, we're no longer in that world. Everything is heterogeneous now. Everything is specialized. And you have memory hierarchy, right? And you have the accelerators. And models are developing all the time. And different models run differently on different accelerators. So you need to know what to run where and for what. If it's training, it's one thing. If it's inference, it's a different thing. And there are differences also in the different inference jobs. There are inference jobs that are more about latency. There are stuff that is more about batching, like summarizing a document. Latency is less important. It takes time. Okay, fine. So you need to support all of that. And what I'm trying to say here basically is we need full stack innovation and optimization. We really need to focus on the entire stack. And the most wonderful thing about working in IBM research is that we actually have work that is doing all of that. I'm going to give you a taste of all that work. We have work on hardware systems. We have work on the platform, on the runtime, on the model architecture, all of that. So innovation to the rescue, system innovation. We talked about the rise of specialization. We talked about proliferation of accelerators. We talked about the fact that the central focus is matrix multiplication, and the techniques that are being used is historic arrays, data flow-based architectures. And the main premise here, and this is what I mentioned before, is the data flow is known in advance when it comes to neural networks. We know the data flow. There are no branches. And because there are no branches, we can do that. We can map it in the best way to the different SMs, the different processors, in a way that will optimize the execution and will hopefully optimize also the energy. what we do in IBM. So we have our own chip, which is called AIU, or actually the new name is Spire, the Spire Accelerator, okay? This is a chip that we built from the ground up specifically for AI workloads. And it's based on a lot of these ideas, approximate computing, representing numbers with a fewer number of bits, the idea of a data flow-based architecture or space-based architecture, where it's data-centric in a sense that you have two different SMs, one for load and store for the data manipulation, another one for the compute, the add and multiply, and it's activated when you have the data available, okay? So it's a sort of different paradigm, and through that, we're able to get a lot of energy efficiencies. We also have other work that I'll get to in a second, but I want to speak, first of all, about this AIU. So it's a very different design point, 75-watt PCIe card. It's optimized for enterprise AI workloads. And so the design point is lower cost or lower energy per token compared to GPU. Today it supports inference. In the future, we're planning for it to support also fine-tuning and training. For this, we need to build the software stack for that. And that's one of the main things that slow us down. And we're going to get to the software stack. I'm realizing that I put way too much material in this presentation. AIU is today integrated into our mainframe, into our Z mainframe. So one thing that happened to me this week is that, and that's real actually, that's actually a true story. I got an American Express transaction. I saw it on my iPhone, but then someone sent me a message and said, from American Express saying, we think it's fraudulent, give us a call. And I'm looking at it and I'm like, what the fuck is that? Sorry for my French. And I'm giving them a call, okay? And indeed, it was fraudulent. It was fraudulent. I don't know how they got my credit card. I actually have no idea. But they knew about it. I actually got the notification before I got the transaction. And immediately the card got canceled. But I'm sure that actually it went through an IBM mainframe. The way it's designed is that there is an accelerator, on-chip accelerator. That on-chip accelerator is integrated in every transaction. Every transaction is checking for fraud. And if they're not sure, then now we're building a PCIe attached accelerator that is also going to be there to support more complicated computations. So it's an ensemble kind of approach where the easy ones you do integrated with the transaction, so the latency is good, and the more complicated you're going to offload to the PCIe attached card. So that's one way that we're using the AIU. The other way that we did is we can also just use it standalone, okay? And we did it with our NASA partnership with a company which is called PreTV, and that are doing the satellite image classification for things such as crop classification and flood detection and so on. And we got some really impressive numbers. So just look here. AIU 2.1 image per second per watt versus 0.6 image per second per watt for a GPU A100. So that's like really good. And there are numbers here that tells you how much you're actually saving, factoring in also things at the overhead for cooling that you don't need. You need less cooling, you need less, all of that. So how much you're saving. So this is really a good proof point. I want to mention two more works. So there is also, and I'm just going to mention them because I don't have any time to go into that. And it's also not my area of expertise. But I did put the links for you so that you can follow and read about them. One is North Pole, which is attacking the von Neumann bottleneck right in the head by just basically getting rid of the HBM memory altogether. There is no external memory. They're inspired by the brain. Like if you think about the neurons in the brain, there is no memory. The computer memory is together. So this is what they're doing there. They're putting there is static RAM in each one of the chips, and they're using this in order to do the computation. And amazing performance, like they can get 25 times more energy efficient for smaller models, And so this is good for like edge devices and things like this. And then analog AI, which is the paradigm of in-memory compute that has other limitations. So it's good for certain computations. We know how to do matrix multiplication, but it has a big problem with errors and so on. So it's not that accurate. Okay. And again, this is sort of in the category of high risk, high reward kind of research. So that's one thing that I wanted to know about IBM research is we do high risk, high reward research, and we do research that is more shorter term, that goes into production, that goes into the mainframe, that have impact in the world, and longer term. But even like when I say shorter term, it's not really shorter term. Like look here at how much work was done and all the papers that were published and all the academic work that led eventually to that AIU going into the mainframe, right? And it's not one size fit all. You know, the North Pole is here in this category: automotive, embedded in the IoT, you know, small devices, doing image processing and stuff like that. AIU, this is data center, and that's integrated in a full solution from the card to the node to the server to the rack and to an entire platform that runs with multiple servers on a cluster. So very different, and this is one of an important principle in our point of view. It's not one size fits all. So don't think just GPU. GPU is like taking the biggest hammer and using the biggest hammer to solve every problem. But we think there is a lot more research to be done on different types of accelerators for different types of jobs. Okay, but heterogeneity introduces complexity, and what we get is divergence in the software stack. And what I mean by that is how do you compile, how do you take that program that you have, that model that you have, and how do you make it work on an accelerator? The problem is with all of this proliferation of accelerators is that there is a lot of work which is required in order to make it work in a real system in terms of the software. So there is a lot of development in the community, and this is why open source is our friend. One is PyTorch, which is really raising the level of abstraction on how you write and how you define neural networks. And then there is also Triton, and Triton is a way to write optimized kernels, raising the level of abstraction and making it easier to write optimized kernels for deep learning. And the idea here is like, look, if I have a new innovation in AI that I want to experiment with, like mixture of experts or something like that, speculative decoding or something like that, and I want to write the best implementation for this. If I don't have Triton, I have to use the operators or the building blocks that are built into the hardware that I'm using, you know, such as a GPU, okay? And that's not sufficient. And if I don't want to use these operators and I need to write really like low-level code, I really need to know CUDA, write low-level code. Very few people know how to do it, and it's very complicated, takes a lot of time. And so not too many people are doing that. So Triton is addressing that gap. It allows you to write these kernels more easily with new concepts, such as the concept of a tile. So it's introducing new concepts. And the idea is that, I mean, where we want to get to is that it's going to support not only GPUs, it's going to support different accelerators. Today, it only supports GPUs, okay? And that kernel community is growing really, the Triton community is growing really quickly. We did some work here to develop some kernels that have like much faster performance, much more energy efficiently. This is work that we did with IBM Research, working together with Meta. So things for quantization, for example, or for accelerating more model inference, a mixture of expert inference, and so on. that is in the community. So this is something that I think is of interest and you should look at. I'm going to touch a little bit about what is a data flow-based architecture. So this is very different than GPUs. Data flow-based architecture means that that I have different threads that are responsible to manipulate the data, the load and store, and to do the computation. Okay, and they can work when you know the data flow ahead of time, which is a situation with neural networks. So in neural network, you usually don't have branches like this. You don't have if, then, else. And that's why you can do that. And they offer a lot of advantages in terms of energy. However, so it's a good thing, and a lot of I think the trend is to go toward data flow-based architecture. However, it requires more sophisticated software stack and compilers, and that's something that we don't have yet. So if we look at that picture here, one of the open questions is like, how do we make it work for different architectures, not just for GPUs? So I'm trying to give you like examples of work that is already done, but also a lot of open questions here. Okay, so now let's move to models. So as I said, the problem with model is the AI scaling or the modularity. Can we use smaller models or combination thereof to achieve equivalent power of expression? I think that's a really, really, really important question that many people are thinking about. There are some techniques that are being proposed, like LoRa adapters is one technique where, let's say if I fine-tune a model, I don't create an entire copy of that model that is now being trained on specialized data that I have in my organization to create something that will work for me. I'm only creating a small adapter. So I'm freezing the parameters of the model and I'm creating a small adapter. So obviously it's the way to go. Obviously this is a useful thing. Lots of questions and open questions that are related to these LoRa adapters. You know, such as, and I had some interesting discussions with the students and with some of you here about you know, how many LoRa adapters am I going to have? Thousands, and which one shall I load where and cache where and so on. So how to manage that in the most effective way. And then mixture of experts, a different approach to the problem, where you take a model and, you know, one of the ways to think about it is decompose it to specific smaller models. And because we talked about the energy being super linear in the size of the model, it makes sense to break it to smaller models. When we break it to smaller expert models, every time that we have an inference job, only one of the experts or maybe two of the experts get involved, which means that the number of parameters that are being activated is smaller, and that means less energy. So that's another way to do it. And this is just two examples of model innovation. Obviously, there is so much more. And as I said, people are thinking beyond transformer and so on, and like it's exploding. But a lot of it is about how can we get the brain, how can we get this intelligence, but not spend so much energy and so much compute. Yes.
You see, like as you're describing now, the model is like innovating much faster. So if you talk about sustainability and the embodied carbon in that area, how far in the future you need to look into when you design accelerator for such workloads?
Yeah, good question. I'll get to embodied carbon. If you let me, I have a chart about embodied carbon. So beyond model innovation, there is runtime innovation, such as how do we train, how do we do inference, and so on. And then there is open questions, completely open questions, such as software and hardware co-design, sparser models and system architectures that are co-designed together. Can we design hardware for the particular neural network architecture? Can we go beyond matrix multiplication and in the hardware architecture and maybe beyond transformer in the model architecture? So this area is very, very interesting and very, very active at the moment. Wanted to mention quickly 2 model innovations that we did in IBM research. One of them is how you grow a model. So we grew a model from 20 billion parameters to 34B. But instead of just starting to train from scratch, what we did is what is called depth upscaling, which means that we're duplicating some of the layers. So we're not starting from scratch. Saved a lot of energy this way. And again, the paper is here. And the other one is self-MOE, self-mixture of experts, which is another technique. It's a specific mixture of expert techniques where the way we do it is we train a big model that is general. And then we generate synthetic data. The model actually generates synthetic data for different domains, such as reasoning or math or coding. And that synthetic data, and that's easier to do than to have some sort of a supervision or labeling or whatever, and created domain-specific experts based on that big model. And then there is a rounding function that every inference job needs to decide which one of these experts to involve, and there is some science there as well. It's another model, basically. But again, the number of in this way, the number of parameters which are being activated every time that you answer an inference job is much smaller, and the energy which is spent is much smaller. I think I need to really speed up a little bit. So runtime innovation, I just want to say, okay, how we do inference? You get into the runtime itself, okay? So VLLM, one of the servers which is used for inference. You get into techniques such as speculative decoding. 2 to 4x improvement with speculative decoding with a technique that we improved on an existing technique. Everything is open sourced. Here's the link here. So 2 to 4x improvement in throughput. But because we're running in like close to 100% utilization, that translates to 2 to 4x improvement in energy. Okay, so a lot of what I'm showing to you here is like it's not necessarily that energy is the first most important objective. I actually just want to run more work. But when I run more work, because I'm running and always in the highest utilization, that means I use half of the resources. Okay, that means I use half of the energy. So it's so the translation here from throughput to energy is pretty trivial. So when it comes to inference, speculative decoding, quantization, dynamic batching is techniques that people are working on. When it comes to training, it's different. It's about parallelism, so fully sharded data parallel. All the techniques for parallelizing, there are 3 different techniques for parallelizing, at least. What we're showing here is we actually took several techniques and combined them together with Meta. And so there is selective activation where you sometimes activate the parameters, but sometimes you just reuse output results from previous activations. So multiple different techniques that are combined gave us much better token per second per GPU. And that was not trivial to do. So there is actually a very good YouTube movie of one of our guys from IBM Research talking about what did it take to actually combine these techniques. Because the thing is, they just don't work together. Nobody tried them. We're the first to try them together. And things break, and you discover gaps, and you need to solve errors, and so on. So it's not trivial to get there. Finally, we get to the platform innovation. So as I said, platform is the glue. It's the thing that makes everything works together between the multiplicity of models and the heterogeneity of accelerators that you have in your infrastructure. How do you optimize the deployment? And really, it's a big constraint optimization, multi-objective problem. You care about latency, you care about throughput, you care about cost. Different accelerators cost you differently. You care about efficiency. You obviously want to have the maximum efficiency.
But you may also have a cap on your energy, and that's real. Like data centers have caps on their energy that they cannot exceed. You care about the quality, accuracy, you don't want to compromise that, and you care about scalability, okay? And so you have this pool of resources. You have inference endpoints, fine-tuning surveys, you have distributed jobs that are part of your training jobs, right? And the kind of techniques that or the kind of areas that we need to look at is how do we do the routing and queuing? Like when a request comes in, where do we send it? Okay, so think about it. Different models are loaded on different GPUs. GPUs now have an XPUs, and I should say accelerators, not GPUs, accelerators. And different accelerators have different sharing technologies. So now you have MIGs, and MIGs are slicing of the GPUs, but you also have time sharing. And maybe sometimes you can combine both, okay? So different sharing techniques. And you have different models, and we already know that models run differently on different accelerators. So you need to profile all of that and understand all of that. And then you need to make use of these resources that you have. You have memory and caching hierarchy, and you're starting to have topology. And what are topologies in this sense? Topology, a mixture of experts is a topology. Even lower adapters, you can look at it as topology because it's like the smaller models that are connected to that bigger model. And now we're starting to see agents. So they're going to be topologies that relate to agents, which is multiple models that are collaborating together in order to solve a bigger problem. So you need to place all of that, and you need to understand when to scale up or down based on what you're seeing in order to make the most use and to make the most use of your resources and your energy. This is an architecture that we're building that shows all the queues and the placement algorithm here, the GPUs and the slicing, and the caching, and the observability, which is really important here. It's how you observe and how you profile. And I don't think I have it. I need to add it to this chart. The profiling, you do offline profiling to understand how models behave on different accelerators. And you always try to stay on the Pareto curve of each one of these models, because otherwise you're wasting something, right? So always stay on the Pareto curve for all these models. Okay, so yeah, I see here, benchmarking service is doing the profiling. Metric service is telling you what's the current state, what's the utilization, okay? And then deployment controller is doing the actual work of automation, and then you have the optimizer here. So this is something that we're building at the moment, and we're experimenting with. But we're already seeing results. Like when you're using dynamic slicing, you can get in some scenarios 50% improvement in the GPU utilization. Caching can really help, and so on. So we're starting to see results here. This is the work. Oh, that's the fun part. I get the collaboration with UIUC. So this is the work, a great work that was done in UIUC in collaboration with by Heron, with Ravi, and people from our team, Hubertus and Chen. And this is a great example. I like it because it's a great example. And what they noticed is unbelievable, very interesting observation. Different models are more or less sensitive to frequency scaling. Frequency scaling is a way to do the power capping, to reduce the power which is consumed. So if you know the sensitivity, then you know which one you can power cap down versus you don't want to touch because it's going to degrade performance. However, it's more complicated than that, because the way frequency scaling works, the granularity is in the scope of a server. So if of a GPU, sorry. So if you have multiple different slices, they're all going to go down or they're all going to go up. So now you need to place all the sensitive ones together and the non-sensitive ones together. So it needs to work together with the placement algorithm. So that's what makes it interesting. And there is much more innovation that I'm not going to go into, but it's a great example of, now that, you know, I showed you a lot of work that has to do with just improving the performance. And by improving the performance, the side effect is that I improve the energy efficiency. but there is some work that is about keeping the performance and just improving the energy. Okay, so there are these opportunities, and there are multiple opportunities to just improve the energy. Also, when we are leveraging parallelism, so there is work that we did also here with collaboration with UIUC in a federated, when you have federated AI, right? And you understand, you do the training, but you understand what is your critical path, then anything that is not on the critical path can be made to run slower. And it's not going to hurt your bottom line, the time to accuracy. It can be made to run slower by reducing the frequency and then reducing the power. Okay? And reducing the total energy. Okay? Because of how energy works. And now I said there is a new academic work that just came out that is actually doing exactly the same thing for LLM. So basically distributed training, and it's doing the same thing there. Okay, so this is very interesting ideas. Actually, Chen presented this in KubeCon. Actually, she presented an integration with Climatic, where she's adding the policy component so that you can now start dialing down and up the frequency for inference, not for training. For training, people are not doing it. But for inference, you can dial down based on the known sensitivity, based on your SLAs, based on the conditions, based on how much renewable energy you have, so you can introduce policy into that system. And that was presented by Chen Wang in the latest KubeCon. And there is much more that we do with UIUC. So there is work on quantification, like breaking and understanding each stage of the inference job, how much energy is involved. There is work in energy-aware placement, and we just discussed with Jingwa several ideas on how to connect this with the LoRa adapters. That was really interesting, right? Graph-based placement, GNN-based, so GNN-based with reinforcement learning. And then there is work about energy-aware compilers that it really fits very nicely into what I described before. Remember the entire thing about the software stack needing to come together in order to support diverse set of accelerators. So how do we actually start with a PyTorch, start with an easy abstraction, but have compilers that are going all the way down, but supporting different types of accelerators? That's like, for me, that's like the holy grail. If we can do that, and if we can do that in an energy-aware way, it's even better. Right? I mean, the accelerators themselves, the whole purpose of these accelerators is to save energy. Now the problem is how to integrate them in a way that they're going to actually be usable. So AI is the problem, but it can also be the solution. So one thing that I want to mention here quickly, we did a lot of work on dispatching based on renewable energy. So you send, so the idea with dispatching based on renewable energy is you send the work, you dispatch work to like your training jobs to where you have the most renewable energy. Renewable energy fluctuates all the time. We don't have control over it. It's based on the wind and sun. We do have control over where and when we run our compute. So it makes sense to match. But after I talked about it a lot and I thought about it and I worked with multiple people in the industry and in the academia, I reached the conclusion that we're thinking about it the wrong way. Because it's not about making us better. I want to consume the green electrons and you're going to consume the brown electrons. That's not going to help anyone. It's really about we can help decarbonize the grid. The problem with decarbonizing the grid is that we want to move to 100% renewable energy, but we can't because renewable energy fluctuates so much. And if we move to 100% renewable energy, then the grid cannot support a certain level of reliability, which we need in order to support things such as hospitals, right? Critical services. Okay, so how do we do that? Well, the data center compute is by design flexible. We can run more or less. We actually have control over it. So if there is less energy and the city needs it in order to support critical services, if there will be in the future a protocol that goes and works between the power grid and data centers, then we can make it work by running less computation. This is a very nice idea. I'm not sure it's practical, by the way, and we're still working on the details, right? The reason why it's not practical is because some people don't want to, a lot of people don't want to waste their GPUs that they paid so much money for by power capping them, okay? So it's a question of the good of everyone, like who is more important or the good of everyone? How do we make it work? And that's where we also need policy, you know. That's where we also need policy in order to make it work. But it could be a solution. So this is another thing I'm thinking about. And finally, I didn't forget your question. We should not forget about embodied carbon. So really, what is embodied carbon? We need to look at the entire life cycle. We need to look at manufacturing, design, manufacturing, transportation, operation, and end of life. But really, where we spend most of the carbon is in the manufacturing and in the operation. And we talked a lot about the operation, but we didn't talk about manufacturing. And you're right that there is that tension. We're building these accelerators and the manufacturing costs. So if I build an accelerator, I want to know that at least it's going to be used for a long time. I don't know that. Or that it's going to be used for many workloads, and I don't know that. So it's a design exploration space that needs to be understood. I had a very interesting discussion about it with Professor Sarita today, exactly about that space. When we go to chiplets, right, then you have more modular units of computing, which are supposed to be more reusable. And there is this hypothesis that they're going to be more usable and for a longer period of time. So that's a good thing for reducing the manufacturing. This is the main problems here. There is some work that we're doing with Columbia and with UIUC on making the design more efficient. And this is using open source tools that Columbia University Professor Luca Carloni built, which is called ESP. And I mentioned already that we're doing, I think I have a chart about it. We're doing this discovery of materials to replace PFAS. And that's actually an NSF convergence accelerator that we're leading in IBM, working together with industry, nonprofit, and other universities. So this is what we're doing for manufacturing. There's much more, which I'm not going to have time to get into, but it's a really important part of the problem. I just don't have time to go into all these all of these topics, but you have the links here. So please follow the links and learn more. And that's it. I really dumped a lot into it, so I apologize for dumping all of this on you, but there is lots of links for additional material.
Great, Tamar, thanks for an awesome presentation. Do we have questions from the audience? We'll take the audience first, but for the online people, please type your question in the chat and I'll take a look in just a moment. So maybe you go first.
Thank you for excellent, talk. I love your picture, which you call the most important picture, right? In your and the right hand side, you had something about beyond the big model or something like this, right? And new innovation.
Beyond big, yeah.
And when you were talking, you still were saying, right, that at one point we still build this huge foundation model, and then we try to either partition or do something else to make it smaller, right?
Yeah.
Couldn't we think about innovation upfront? Right? To start with smaller, which give us what we really want. I'm not saying simple things like starting everything from scratch, but maybe there are some ways of thinking about this way rather than saying, because who's going to build this large foundation model? You can build,
right?
IBM, Meta, Microsoft, but we are not. Probably.
Absolutely. And I think that's going to happen. And there is a huge debate right now, and a huge effort to show that smaller models, when they are trained on specific and high quality data, can really solve your problem. It's all starting with what problem are you trying to solve with the model. And I believe that, and I more than believe, I know that enterprises are going to train their own models. And sometimes they're going to start from scratch. Sometimes they're going to start from some open source model, but they're going to build their own models. So yeah, we need to go to smaller models, and there are multiple ways to do that.
Okay, so I'll try to go somewhat in order I saw them. Let's go to you next, and then find around.
So now people are looking at more intelligent inference.
Yes.
Putting intelligence in the inference some reason, and that will increase the computation quite a bit. all these accelerators will have to be redesigned
Uh-huh.
for that. So what's the answer to this?
I don't know. I really don't know. I mean, I think really this is AI. I mean, for me, it's really just starting. There is so much that is going to happen in the future. It's not just that. There is also agents. And there is also, the agents are interacting with each other. So you have an agent, it's calling out, it's getting an answer based on that, it's doing something else. That's going to be also inside your inference, right? So there is a lot that is going to happen. How to build the accelerator for this, it's a really, really, really good question. And I think some of the ideas is, I mean, for example, when I talked with Sarita, is building smaller accelerators for very specific functions and then being able to combine them. The hypothesis there is that if it's smaller and it's a very specific function, it's going to be more reusable, right? Because you don't want to build a big accelerator for an algorithm that you have, and suddenly that algorithm is useless, right? Because there is something better. So the modularity here is something that could be a potential solution to this problem. But again, what to put in software versus hardware? It's a huge question. I think we're starting with software, and we're starting with experimenting with software. Then we're using that Triton idea to experiment quickly with optimization, using the hardware functionalities. And then we see what we burn into that actual accelerator in hardware. No easy answer here.
Okay, let's do you next, and then I'll swing back to this one from here.
So, the title of the talk is the AI energy problem. And I'm trying to understand what is the energy problem.
Mhm.
It is either a capability problem, which is that they want to do something
Mhm.
and they are not able to do it
Mhm.
because it costs too much energy. Or it is simply an expense problem that
Mhm.
they would much rather do something in $1 which is costing them $2.
Mhm.
So they want you to do.
Well, there is even a third issue.
Yeah, or there is a third thing, which is more, call it, impact on the environment, etc. And the society or the regulatory system wants them to, bring these costs down. So in each of these cases, the problem means something different too. For example, if you focus on the second one, well, if they think that they're providing enough value, providing enough output versus the input, then well, that second one is not so much of a problem. And it seems that way, right? Because considering the amount of investment
Which
that
is
they
not the case today, but okay.
no, considering the amount of investment they continue to
Mhm.
get. So for you, when you think about the AI energy problem, which of these three problems are you most concerned about? Because especially the second one, it doesn't seem to me that folks doing the AI.
I'm not concerned about the second one. I'm concerned about the first one and the third one. I'm concerned about energy because there is not enough energy. So, and because inherently from a scientific standpoint, it's interesting because we develop a technology that doesn't scale. The technology doesn't scale. How do we make it scale? That's an interesting scientific problem, okay? And I'm concerned about energy because there is just not enough. And obviously I'm concerned about Earth because I love Earth. So I'm not concerned about cost because there are too many companies with a lot of money there. So it's not my concern, but I'm sure that other people in IBM may disagree with me, and our clients are going to disagree with me. I mean, they really care about cost.
That's in the interest of time. Let's do two more. Let's do you, and then you, and then.
I just want to poke a little harder on the idea of the full stack,
Yeah.
right? Because I want to think of the full stack as including the solar farm on the outside and the battery building and the transmission line, the power plant, the internal feed to the racks, the 1 volt going down to the chips. And of course, at the end, when we're all done, all we've really done is generate heat.
Right.
And somebody has to
Absolutely.
deal with that too.
Absolutely.
So how, talk a little bit more about thinking of that full stack.
Yeah, look, you're absolutely right. It's just like, I can't talk about all that in 1 hour, but obviously there are people that are working on how to do power conversion more efficiently, how to do cooling more efficiently. There is liquid cooling, there is techniques there. There is how you generate the energy. It's also part of that. So yeah, it's all of that. I just cannot talk about all of that in one presentation because it's gonna be, you choose the level that you're comfortable to talk about.
Well, and just to add a little comment, the thing you were talking about was a variation of trying to manage the power flow. On the power side, we would call it a virtual power plant or virtual storage.
Yeah.
Right, because you're trying to emulate the dynamic action of the resource
Right.
by manipulating the end use, the load.
Right. Exactly. Yeah, exactly.
Right, next maybe you can ask a question.
Yeah, thanks for the talk. So you mentioned at some point that specialization in architecting chips and accelerators and also looking for new models other than transformer. Like both of these things are somewhat happening already right now.
Absolutely.
So my question is, eventually you want to go to like UI agent, right, which can do not just one task or two tasks. You want something on your phone that can do as many tasks as possible, like another brain, right? So you want one model, and then you also want a chip or one chip which does everything as fast as possible or as efficient. So is specialization actually the way to go? Because it seems like it's already happening and it's not the answer.
Let me give you, so there is system on chip. There is a chip that has multiple different accelerators, and these accelerators work together. So some of them are better in video processing. Some of them are better in encryption, decryption. Some of them are better in language, okay? And they're working together. So system on chip is already happening, okay? And this is what is used there. That's what's going to be used in, for example, for automatic vehicle, for self-driving vehicle. And then there is a move to chiplets. So one doesn't contradict the other. Okay.
Okay, so before we conclude, I want to take the Zoomers into account. We have one question on Zoom, and that is from Brighton Godfrey saying, to reduce AI energy, to what extent do you see unsolved challenges related to networking? Or is the network typically doing well enough?
No, it's not doing well. No, I mean, there are problems with network. So, I mean, I think I don't know enough to talk about it. I think that you can talk about it in different levels. There is the level of actually what's going on inside the system. So I talked a lot about the data movement between memory and processor, but then there is the next level of how the chip is integrated into a full system. And we've investigated a lot in IBM research in basically saying that the network is the bottleneck. There is the network, there is the data movement, there is how to reduce data movement, there is memory hierarchy where you have the cache and you have the non-volatile memory and you have the object storage and so on. They sort of all need to work in tandem. But one thing that we did, and I'll be happy to send a link, is came up with an architecture that worked for us, which we called our Vera supercomputer, that is dealing with the network in a very innovative way. So if you just Google Vela IBM, I think you're going to find it, but I'm also going to be happy to send a link.
Okay, great. So if you want to chat more with Tamar, she'll be around. But for now, let's thank her again for a great presentation.